Today I am here to present on my research article titled Slenderness in Steel Fibre Reinforced Concrete Long Beams. This paper has been awarded as the Best Research Article Award by International Research Excellence and Citation Awards Committee. Firstly, I'll give a brief introduction about myself. I am an academician of about 9 years experience. I am currently serving at STT University in the Department of Civil Engineering as an assistant professor. I am a gold medalist in my Masters of Technology in Structural Engineering. I'm a research scholar at IKG Punjab Technical University, India. This research work, which I'm going to present here, is a part of the research work I carried out during my thesis. So, let's start it. Slenderness in steel fiber reinforced concrete long beams. The reinforced concrete beams are designed according to IS 456-2000, that is Indian Standard Codes for reinforced concrete structures. The dimensions, or say the span, is decided according to the Indian Standard Code. But the response of long beams is very different as compared to the normal span beams. Long beams fail by destabilization. Past research concludes that the slenderness limit for this reinforced concrete beams in the design codes cannot predict the behavior of reinforced concrete long beams. Further research has laid down that the slenderness depends upon the values of ultimate flexural moment capacity and critical buckling moment. To find out the slenderness limit, we should precisely estimate ultimate flexural moment capacity and critical buckling moment capacity. Now, what is concrete? Concrete is the mixture of cement, aggregates, admixtures, and water. Concrete is the oldest building material and is most extensively used. Why? Because it has high compressive strength, durability, and stiffness under severe environmental conditions. But it has a demerit. It has low tensile strength. This tensile strength can be improved by providing steel reinforcement. This steel reinforcement is provided in the form of steel bars which guard against localized tension only. Now, because these steel bars guide against localized tension, for overall providing the tensile strength to the complete beam, the solution is to provide steel fibers. Why? Because steel fibers act as crack arresters, since they are uniformly distributed and oriented in a random fashion. Now, the advantages of steel fibers are many. First, it gives excellent tensile strength. It has good shock resistance and ductility. It has a crack arresting property and provides good flexural fracture resistance. This reduces the crack width substantially. The type of steel fibers which are available in the market are, according to their shape, they are straight, hooked, button-end, indented, puddled, and crimped. To maximize the benefit, fibers are added by weight in a particular range for its durability, increased load carrying capacity, and structure integrity. But they have a disadvantage. They can rust, so they should not be provided at the surfaces. Concrete, when reinforced with steel fibers, becomes steel fiber reinforced concrete. Conventional reinforcement may be given or may not be. Now, steel fibers in concrete improve the flexural fracture resistance of the reinforced concrete beams. Therefore, reinforcing these reinforced concrete long beams with steel fibers might improve the strength of these beams. Use of steel fibers in the building sector is limited. Why? Because of the lack of technical standards in the legislation. Design codes are completely silent on the effects of slenderness in the steel fiber reinforced concrete long beams. Therefore, the objective of this research is to understand the slenderness in steel fiber reinforced concrete long beams and provide a mathematical model for the limits of slenderness for these SFRC long beams. Now, to find the slenderness for these SFRC long beams, we must estimate critical buckling moment and ultimate flexural moment. Since design code is silent on this, there's no approach for calculating critical buckling moment for reinforced concrete long beams. There's no formula for predicting ultimate flexural moment for SFRC long beams. Now, there are researchers like Revati Menon, Girija Menon, who successfully predicted the critical buckling moment and slenderness for this RC long beams. Revati and Menon found out that the slenderness limits as presented by the IS 456 are not reliable, and the failure occurred by instability if applied to RC cylinder beams. So they proposed a formulation to predict critical buckling moment. The expression for limiting slenderness ratio was explicitly derived for under-reinforced rectangular reinforced concrete beams. The proposed expression for limiting slenderness ratio accounts for beam end conditions, loading conditions, concrete strength, and steel, as well as tension and compression reinforcement and transverse reinforcement ratio. A wide range of slenderness limits is feasible for different set of design variables, in contrast to the constant value prescribed in the existing codes of practice for specified end conditions. Reinforced slender beams also exhibit deflection effects, lateral deflection and twist, even at moderate slenderness. That was concluded by Revati and Menon. Now, Girja Menon modified the formula for critical buckling moment presented by Revati and Menon, and it took into account the non-linear behavior of concrete, which was responsible for the development of cracks, and provided a formula for calculating the slenderness ratio, which gave more accurate results. Now, what does steel fibers do? Now, steel fibers, ultimate flexural moment for reinforced concrete beams, can be applied to reinforced concrete long beams, but not to SFRC long beams, because it is silent on the addition of the steel fibers to the reinforced concrete. The formula for calculating ultimate flexural moment of SFRC beams was proposed by Singh, which sufficed with the lab test. No mathematical model for slenderness limits, and hence to accurately predict the behavior of SFRC long beams, is present. The present study aims to present an analytical equation for predicting the slenderness limits of these beams. Now, Singh studied the ultimate flexural moment of RC long beams according to IS 456 and found out that this cannot be applied to SFRC long beams as it is silent on the effect of adding of the fibers to the reinforced concrete. So, mathematical model for predicting the flexural strength of SFRC beams using wide range of experimental data was devised, which took into account the real contribution of steel fibers and concrete and their interactions. However, the formula for calculating the ultimate flexural moment capacity of SFRC beams was suggested, which sufficed with the lab test. The steel fibers, Musa found out that the steel fibers incorporated into RC beams would serve as crack arresters in flexure, and experimental test results supported the hypothesis that the cracking in flexure was controlled. Wang and Gao said that the compressive strength effect of steel fibers on the compressive strength is negligible. The methodology which was followed in this research is that the relevant literature and codal provision for reinforced concrete long beams, for SFRC beams and SFRC cylinder beams were critically analyzed. The details of the experimental program was worked upon, that is, the size of the test beam was defined, the type and size of steel fibers, and the percentage of tension reinforcement and the grade of concrete was decided firstly. Theoretical formulations for assessing the flexural response of SFRC long beams was worked upon. The results from the theoretical investigation were compared to the experimental investigation, which were found to be in accord. Hence, the theory was suitably firmed up. Therefore, the theoretical framework for assessing flexural response of SFRC long beams is suggested. Finally, slenderness limits for SFRC long beams is proposed for possible incorporation in design codes. Now, the specimen details. The dimensions of the beams were selected such that their slenderness exceeds the region of limits as proposed by IS 456. Considering the practical difficulties in casting and testing very long beams, the span was limited to 5 meters, and hence the width of the beam was decided such that L by B was more than 60. Therefore, the width of the beam was selected as 80 mm. Upon deciding length and width of the beam, the depth of the beam is decided exceeding the slenderness ratio from IS 456 as LD by B square should be more than 250. The beam size was selected as 80 mm into 360 mm into 5000 mm, that is 5 meters. The L by B ratio of the test beam was 62.5 and LD by B square is equal to 253.125. Cement which was used was normal PPC of Ultratech and OPC 43 grade. Fly ash class F was used. Silica fumes for high-grade concrete was used. Steel bars with Fe 500 and stirrups of Fe 415 were used. Coarse aggregates 12 point maximum size of coarse aggregates was 12.5 mm. Fine aggregates zone 2 was used. Water was locally available. Steel fibers which were used in this research article were hooked end with aspect ratio 63.63 and 77.78. And super plasticizer which was used was Fosroc Oromix 400. This you can see the reinforcement details, how the reinforcement was designed and how the stirrups were placed. The distance between the stirrup to stirrup was 75 mm. Now, these are the in-depth detail of the reinforcement, how and what was the depth and what was the distance between them, everything is shown here. The materials, these are fly ash, silica fumes, and this was the dry mix which was formed after mixing everything, coarse aggregates and fine aggregates. All the prior lab tests were done, conducted on it, and when they passed through the normal Indian standard codes, then only they were used. Now, these are further details after conducting the basic lab test. The finest modulus of fine aggregates was 1.98, specific gravity 2.6. Then for coarse aggregate also, the maximum stone size was 16 mm, finest modulus was 4.96 and specific gravity of 2.97. Cement which was used was PPC and OPC, both from Ultratech brand. Fosroc Oromix 400 was the mixer used. It was available in the lab itself. Now we tested on 3 grades of concrete. M1 you can see, that is the normal M25 nominal mix. Then nominal mix for M25, but this is the actual design mix which is presented over here. Next is M2 for M40. M40 was what we decided that it should get the strength of this. Then upon testing the cubes, we found out what the strength was, which is available in the lab test, actual lab test data. Now M3, the design mix is as presented here. Then the steel reinforcement, as already discussed, it was Fe 500 and stirrups as Fe 415. These are the type of steel fibers. These are hooked end. 0.45 is the dia, 35 mm is the length. And the second one is 0.6 mm is the dia and 35 is the length, 35 mm. The experimentation method. The 4-point bending test was performed in the heavy testing laboratory. 9 under reinforced rectangular beams were casted. Beam size as discussed was 8360 mm into 5 meter. 3 batches for 3 concrete grades were used. M1 31 to 36 Newton per mm square, M2 42 to 44 Newton per mm square, and M3 55 to 59 Newton per mm square. For each batch, one control beam was designed, casted, and tested. Other were 2 to each, for 2 to more each batch for steel fibers. The remaining sample with 1% steel fibers, hooked and shaped with 2 different aspect ratio were taken. Beam were simply supported and torsionally restrained. The experimental arrangement was based on Hensel and Winter study. The beams were loaded symmetrically with 2 2-point loads at the middle third span locations. Initial imperfections were recorded and they were in the range of 1 to 6 mm. Preliminary test was performed with the load setup to guarantee that the imposed loading only marginally restrains the beam's lateral deflection. Dial gauges with 0.01 mm accuracy were used to measure the lateral and vertical deflections. So this is the lab setup. This is the beam which is placed that is torsionally restrained, and these are the loads being put up. And here you can see there's a lateral deflection, that is the initial imperfection which we said at the center. Now there's a next table which presents the initial data for the test. Now the test beam data, it's presented over here. The dimension is same throughout. The fiber type, there are 2 fiber types as said. The first one is the control beam. M1SO, M2SO and M3SO are the control beams, and others are reinforced with steel fibers with the initial conventional reinforcement. The conventional reinforcement is same throughout in all the beams for a better comparison purpose. Now, what was observed was there were 3 modes of failure which was observed. The first one was flexural tension failure. That is, negligible lateral deflection was there. When the cracks appear due to flexural failure, lateral deflection is 0, or actually it was negligible, generally observed in the soffit area, extended gradually to both the sides under the application of the load. These cracks propagate upwards, thus leading to final collapse due to concrete crushing in the compression zone with prior warning. Second case was flexural failure with enhanced tensile capacity, that is with the lateral deflection. When the flexural cracks appear due to the application of load with controlled lateral deflection, the cracks generally observed in the soffit area extending gradually to both the sides under the increased loading. These cracks propagate upward similar to case 1, but in this case the beam can take the load compared to the calculated capacity, thus leading to the final collapse due to increased vertical deflection due to bending with prior warning. Failure due to instability when the beam is not able to carry further load due to large lateral deflection or increased twisting with loading and cracks. The failure occurs suddenly as the beam moves out of the load assembly. If you can see, the beam has moved out of the load assembly due to large lateral deflection. If a little more load and it would have just upturned. And the failure occurred at a load value less than the calculated flexural load capacity of the beam. Now this is the experimental study. The test results are there for the experimental peak load and the observed failures. And then we'll do the comparison for all the 3 grades. For all the 3 grades, for grade M1, we have seen from this we have seen the lateral deflection part and the vertical deflection part, that how all the 3 beams differ for grade M1. That is, one is the test beam, the other one is the hooked end with 63.63 as the aspect ratio of the hooked end fibers, and the other one was 77.78 hooked end steel fibers. So we have seen there's a significant improvement seen in the load carrying capacity and the ductile response with the inclusion of the steel fibers. The flexural strength enhanced upon adding the steel fibers. See, the load carrying capacity has enhanced. We can see beams with hooked end fibers having aspect ratio 63.63 shows better response as compared to the beams having hooked end fibers with higher aspect ratio. Now, for this comparison of the load deflection curve for M2 grade, we can see the control beam shows a higher load carrying capacity. So no significant increase in load carrying capacity upon the addition of steel fibers for a minimal grade. That the designed value was M40, around M40 for that upon addition of steel fibers, but there is a good ductile response in SFRC beams as compared to the control beam. The beams with hooked end fibers with higher aspect ratio show minimal improvement in load carrying capacity as compared to the control beam. Now the third case, when we have tried casting a high grade concrete, so the high strength control beam shows significantly reduced load carrying capacity due to slenderness effects in terms of lateral deflection. So this was iterated by Sieve that the beams with higher grade of concrete are more prone to instability failure to that of the beams with lower grade concrete. Steel fiber reinforced concrete beams failed due to instability and showed significant reduction in flexural strength. Lateral deflection were observed such that the beam moved out of the load assembly. The beams with hooked end steel fibers with aspect ratio 63.63 show better ductile response and increased flexural strength but failed due to instability. Now here is the comparison of load deflection curve for different fiber type S1. That is that there is a variation of the concrete grade. Hooked end steel fiber with aspect ratio 63.63 tend to show better ductile response and increased flexural strength for both low and high grade concretes, that is M1 and M3. But when used in high grade concrete beams, it cannot avoid instability failure as it could not help in controlling the lateral deflections. Then when we compared the second type of fiber, that is hooked end with 77.78 aspect ratio, it showed that this fiber type exhibited much better flexural response and ductility when used in M2 grade of concrete. Therefore, it can be inferred that higher aspect ratio hooked end fibers show increased flexural capacity and ductility when used in M4. Next, we will be proposing the theoretical formulation or the mathematical model. According to the literature of RC long beams, it was understood that these beams exhibit different flexural behavior from the normal span beams due to manifestation of the effects due to slenderness. These slenderness effects show up as lateral deflections and twisting, which may cause instability failure without any prior warning. Although the eventual failure may include the yielding of tension steel, slenderness effects are likely to manifest and affect the beam's flexural strength. From the developments in the research related to instability of steel beams due to lateral torsional buckling, the generalized slenderness limits for steel beams, as presented by Kirby and Nethercoat, are presented. Now, the same concept is applied to reinforced concrete beams, substituting the plastic moment capacity with the maximum flexural moment capacity. When lambda is less than 1, the flexural mode of collapse is estimated to prevail. And when lambda is more than 1, the instability of mode of failure is likely to occur. Though the relationship between the two modes of failure can be predicted, in addition to decreased moment capacity for lambda is equal to 1. Therefore, the expression lambda less than 1 is proven by the existing laboratory data and is proposed on the basis for attempting to prevent abrupt destabilization in RC cylinder beams. Design codes impose limits on the slenderness of the beam to ensure lateral stability. In design practice, dimensions of the beam are proportioned such that their slenderness ratio does not exceed these limiting slenderness values. In order to propose appropriate limiting slenderness ratios for SFRC beams, that is to prevent failure without warning, it is necessary to have an accurate prediction of critical buckling moment and ultimate flexural moment capacity. In this part, a simple expression for predicting the flexural response of these SFRC long beams is proposed. Based on this expression, a theoretical basis for slenderness limits is arrived at, accounting for the design variables such as grade of concrete, steel, and amount of longitudinal and transverse reinforcement, type of steel fibers, their aspect ratio, and their volume percentage. Now, this is how we have done our theoretical formulation. Now, potential energy considered as constant. On the application of load, the deformation takes place in both vertical as well as in the horizontal direction, along with twisting of the deformed section, as is seen from the picture from the lab test. This is the picture which we have here. We have presented the cross section of the midspan of the long beam in laterally deflected position. And you can see the lateral deflection is presented by U, vertical deflection by V, and angle of twist as theta. Where U is the sideways deflection, theta is the measure of twisting angle, P is the entire load transmitted, A is the distance of the load applied above the shear center, and mx is the bending moment owing to the load application about the principal bending axis. The expression for critical buckling moment reduces to this equation as presented below. Now, when this expression is applied to RC beams, we can see, and here it has been accounted for cracking and non-linearity of the material. Girja and Menon presented this. Now, this formula for a critical buckling moment can be simplified further, which can be applied to the number of loading conditions and boundary setups, such as this one. Now, how we have to find out constancy, we can see over here from the values of the load. C2 accounts for the beam support conditions, C3 accounts for the position of loads. Now, the critical buckling moment is again found out when the Revati and Menon formula was further revised by Girja and Menon to account for the nonlinearity and cracking of concrete. We came across this effective flexural rigidity and torsional rigidity coefficients. The flexural rigidity coefficient additionally compensated for the tensional hardening effect. As demonstrated by Girja and Menon, it is mostly influenced by the amount of reinforcement in the tensile zone and very slightly by the strength of concrete in the compression zone. Right? So next, it was again by Tang that the expression was further simplified. Therefore, the equation of critical buckling moment was derived at by simplifying and is presented over here. Now, for critical buckling moment, we have found out for the estimation of ultimate flexural moment capacity for SFRC. Now, we will see the expression. Concrete beams collapse due to the crushing of the concrete along their path, regardless the amount of reinforcement given. Now, the reason is its low tensile strength. Bars give localized tension only, and for controlling the cracks to propagate, crack arrestor is required. So, steel fibers work the best and impart ductility. Now, when Singh derived the formula, volume percentage of the fibers was VF, fiber aspect ratio L by D, that is, this is for the fiber length and fiber dia, utilized in the concrete mix, increase the capacity. FCK has minor effect on fiber index value. SFRC beam with an increased fiber value is predicted to have a greater flexural capacity. Consequently, in case of flexural steel fibers concrete reinforced member, the traditional tensile reinforcing bar in its tensile region are given, and as they offer mobilization and play a vital role in adjusting the location of neutral axis in the segment based on the strain value, consensus at the reinforcing bar level. They increase its flexural capacity, tensile capacity with regard to the inclusion of the steel fibers existing in the tensile area. Now, this is how we have found out the expression for ultimate flexural moment capacity for steel fiber reinforced sections. Now, Singh presented flexure model to estimate the ultimate capacity of steel fiber reinforced rectangular section. Volume fraction VF determines the portion of volume of steel fibers in a beam to total concrete volume of that beam. Aspect ratio, as discussed, is the length of the fiber divided by its diameter. Steel fibers are dispersed randomly and displayed uniformly throughout the beam. For presenting the realistic model of steel fiber reinforced concrete members, Singh took into account the conventional reinforcement, that is steel fibers in the spanning in the length of the beam with the cross-sectional area AST at a distance D dash, as you can see, as you can relate from the diagram here in the slide, from its bottom face as shown, in addition to the steel fibers. Now, this is the expression as presented by Singh for the flexural moment capacity of SFRC members. Now, this expression was derived by Singh. Now, here we have just put the values of H1 by D, H2 by D, and we can see the fiber index here. And just substituting equations, we derive at a simplified version of this. Since we have already discussed this, that lambda less than 1 should be considered, and here just the squaring part and little mathematics we apply on, and we derive here at this solution. LD by B square, we can see should be less than this. But next part we'll see here. But according to IS 456, RC simply supported beam is proportion such that the span of the beam should not exceed 250 b square by d. So we have the other higher value, that is L should be more than 250 b square by d. So the final expression for slenderness is presented here, and this we can see that the comparison, first we will see the comparison of the test beams, that they validate the experimental and theoretical test beam data is validate or not, because this test beam data is validated as presented by Girja and Menon. Just the RC long beams formula were applied, and we see that they perfectly validate. And then whatever we decided is shown here. Lateral stability of RC cylinder beam suggested by Girja and Menon holds true when applied to control beams. Formulation published can further be applied for assessing the flexural response of SFRC long beams. Therefore, the formulation can further be applied for assessing the flexural response. Further theoretical expression can be derived for assessing the flexural behavior and relationship between the different dimensions of the beam. Can be suggested in terms of slenderness ratio of steel fiber reinforced concrete long beams, which must be validated further for all the laboratory tests performed on the specimens of SFR. The next slide shows the results. Now, the conclusion is formed that existing formulation for slenderness limits do not predict accurately the ultimate moment capacity and mode of failure of rectangular SFRC beams, as the contribution of steel fibers is not taken into account, which affects the flexure moment capacity as established by the 9 experimental tests conducted in the present study. A theoretical formulation for slenderness limits for SFRC long beams is being proposed, which has been validated against experimental tests performed in the study, and the data has been presented in the next table. Limiting the slenderness ratio lambda less than 1 is suggested on the basis of avoiding sudden instability failure in long RC beams, as by Rafti and Menon for long RC beams. Simplified expression for limiting slenderness ratio is proposed here. The high strength SFRC beam show instability failure in the form of bending and twisting. So the load carrying capacity of M40 grade of concrete shows better results than M55, as M55 grade shows twisting and bending leading to instability failure at lower loads as compared to its load carrying capacity. M40 grade shows better results as compared to M25 grade of concrete, as M25 shows lower value of load carrying capacity as compared to M40. The higher aspect ratio of steel fiber shows higher load carrying capacity of M40 grade of concrete, unlike M25 and M55 grades of concrete, which show higher load carrying capacity with lower aspect ratio for the same fiber type. No shear cracks were observed. All the beams failed in flexure. The mode of failure as predicted was based on the theoretical formulation is same as proved during the experimental testing. So the theoretical formulation predicts the behavior of the beams accurately and can hence be applied to SFRC long beams. A better deflection control both laterally and vertically is shown by the beams with hooked end steel fibers with an aspect ratio of 77.78 as compared to the hooked end fibers with an aspect ratio of 63.63 as inferred by the load deflection curves. The failure in the grade M55 of SFRC beams was due to instability because of the twisting of the beams and increased deflection, leading to beams moving out of the load assembly. So here are the conclusions, and if there are any queries, please feel free to email me at this. Thank you.